Okay, thanks. All right. So, a quick recap of yesterday. So we derived these differential equations. I'm calling this also mu square plus a quarter. And likewise the delta V equation. Okay, delta V plus. And you can solve this equation, find the particular solution through Frobenius method, just by power law, matching coefficients. And I illustrated yesterday that if you take, there's this, we call the harmonic, I didn't say it yesterday, but let me just say it. We call the harmonic oscillator limit. You send U and V to 0 with U and V fixed. And then we were getting this equation that once you introduce this variable psi equals e to the t, it looked like this, right? dt squared plus mu squared, some rescaled, just some harmonic oscillator with a kick. And the last thing we discussed is that you see there is a naive EFT expansion, a large mass, which you would write f of u and v as, let me send mu to infinity. You write it as 1 over mu squared uv over u plus v plus maybe minus delta u over mu to the fourth uv over u plus v plus ta ta ta. But you would miss misses from the zero modes or homogeneous solutions. E to the minus pi mu corrections. So we don't need to do perturbation theory. We can solve it exactly. And I showed you in this harmonic oscillator limit how if you try to build a solution that is valid everywhere, when you do gluing of perturbative solutions that have a natural mass expansion at small kinematics and large kinematics, if you try to build it in all the kinematic space, you are forced to introduce these exponentially small pieces. Okay? So, by the way, this is a side remark, but why did we put, remember that uv divided by u plus v is 1 over e total, which is the simplest contact interaction, right? So why can't we put something more complicated on the right hand side? Why can't I put, for example, delta u squared plus a delta u? Can I do this? Does it change anything? There's a question. The pole is here. So let me remember that the analog in scattering amplitudes is that S minus m squared times scattering amplitude equals the uv over u plus v is just E total is the analog of G. Now here would be like GS, G1S plus G2S squared, okay? So do I get the new exchange solution? Is this a naturally distinct signature of an exchange of a particle? Well, we are saying that there's a unique exchange solution. There's a unique function that characterizes exchange of a new state. I just showed you in flat space, the analogy was with this, right? S minus m squared. So this function is the cosmological analog of this scattering amplitude here, okay? Exchange. What about this? Is it a new exchange solution? You could have said, well, you know, the cubic vertex is a little bit different. It has derivatives and so on. Therefore, the exchange solution differs. Is it true? I mean, what's the true signature of an exchange? The pole, exactly. So you just read off the residue. As s goes to m squared, what is the residue? It's like g1 m squared plus g2 m to the fourth divided by s minus m squared plus contact interactions. Okay? And this you can just call G. So the true signature is the pole. So you just, you can rewrite the answer as contact interactions. You can decide to just put under the same denominator the contact interactions and the exchange, but the true signature of exchange of a particle is the pole. Okay? So how do you solve that puzzle there? Same thing. Write F tilde equals F plus, well, let me not overcomplicate things. Let me just keep this first power and erase this, okay? F plus alpha uv over u plus v. Plug it on the left and on the right. What do you, sorry, on the left, what do you get? Delta u plus mu squared plus a quarter F plus alpha delta u uv over u plus v plus mu squared plus a quarter uv over u plus v equals delta u. So you just set alpha to 1. These guys cancel. You put this on the right hand side and you back to the original equation, okay? The point is that uv over u plus v is not delta u of anything, right? So it's so you can't keep on doing this forever. It stops here, the simplest contact term. By the way, this is an interesting question. Huh? So this guy here is, you could have just written down it's a cubic u plus v cubed, it's a numerator, but it is delta u of something that only has the total pole. But you can't do it here. What is the interpretation of if you tried to, in other words, if this were delta u of something, it would mean that there will be a g for which this is true. So what is the interpretation of G? Let's keep undoing. So the contact terms become more and more irrelevant, right? So C0 is uv over u plus v. C1 is delta u C0. C2 is delta u squared C0. And the singularity structure never changes. So why can't I say, well, C0 is delta u of something? Why can't I say that? What do you think G would be? The answer is on the board, okay? It's the first equation I wrote today. So what is G? What is G? Guys, let me help you. If I put G here, what do I have to do to this equation so that it's equal to this one? Whole sentence. What do I have to do to this equation to get there? Echo. Okay. M squared equals 2h squared. Exchange. It's an exchange solution. It's just the fact that these are powers of Mandelstam, right? So S flat squared, S flat. C naught is S flat to the 0. If you kept on doing, you get 1 over S flat, which is the exchange, massless exchange solution. Okay? So it's the exchange. But now, you see, in cosmology, if you try to do that, remember that delta U has these other singularities in E left and E right. So this will come in with new singularities. It's going to have the E left, E right singularity, and the E total singularity, unlike all of these guys here. So that's the true signature of exchange. There are extra singularities in the answer. Okay? All right. So enough about this equation. What does the answer look like? You can plot something like this. Log U, and just to rescale so that things look nice, I'm gonna keep V kinematics fixed. I'm gonna work at the fixed V just to show you. And then here I start from, say, the square, and then as I go in this direction, I'm squeezing. Okay, I'm making U smaller. V is fixed, so the perimeter on the right is V. It's 1/2, and then I'm making U smaller, so I'm just squeezing here. Okay. So remember, in this case, all the modes have equal wavelength. Perturbations were created at the same time. You get equilateral-like non-Gaussianity, and it's well fit by effective field theory. So the answer looks rather boring. Actually, the signal peaks here. It looks like it's going to 0. Maybe that's not the right way to. Let me. It's because of the U to the -1, okay? But the signal is really the strongest here, just because contact interaction. So this is the effective field theory part. You're just seeing self-interactions. And then remember that in the soft limit, it looks like a forced harmonic oscillator, at least if the mass is big enough. So the mass needs to be bigger than 3/2 Hubble for you to see these oscillations, remember? The mass is too small, you're gonna see just some critical or underdamped harmonic oscillator. But for the massive case, the most spectacular, because you see, and here it's blowing up just because of the u to the minus 1. You see oscillations. Okay. And this is the particle production. So that's how you detect new particles in the sky. You would look for these little features. Of course, this is u to the minus 1, so the real signal looks more like this, the EFT part. There's a big EFT part, and then when it's not that you hit a resonance, it's that as you look at bigger and bigger scales, the resonance has enough time to pick up a phase. Okay? That's what the answer looks like in the actual F. So, well, let's contrast with scattering amplitude, cross-section in a collider. If you plot the center of mass energy, how do we detect the Higgs or W bosons and so on? So you have, some effective interaction, Fermi theory of fermions, and then the cross-section grows slowly, like a power law. You fit the Taylor coefficients with effective field theory, and then when you sit at a certain energy, you see a big spike, you see a resonance. Okay, so the location of the resonance, so that's where you see particle production. And then as you move away from the resonance, you get again some effective field theory, but now tilde because you need to integrate in this new particle that you detected. Now your energies, so that this new particle is active, it can move around, so you cannot just leave its effects as irrelevant operators. So here in cosmology, the experiment is run at fixed energy, h. The way we detect new particles is by dialing kinematics. And the decay rate of the signal will tell us about the spectroscopic properties of the particle. Okay, I'm gonna discuss the phenomenology in a second. Let me say one more thing about the answer, which is the analytic structure, which is kind of neat. Well, this is the actual correlator multiplied by some factor that is blowing up the signal, right? So the real signal goes like this. It's decaying. There's some envelope. The envelope is related to the fact that it's a matter particle, so it goes like 1 over eta cubed. Sorry, it goes like eta cubed, the signal at late times. So if you give enough time for it to propagate, the signal is being redshifted away. But then this is the envelope, and then the oscillations on top of the envelope are related to this, to how much above 3/2 h the mass is. Okay, so that's but I'm gonna get back to phenomenology in a second. Okay, something about the analytic structure. At fixed V, fixed physical V. So if you plot here the U plane, real and imaginary, then I used to be better at this. Let's see. That's better. Okay, so remember that the differential operator had three singularities, three singular points, 0, 1. But at 1, we demand that there is no singularity there. So the solution is move. And then minus 1. At -1, there is factorization. At 0, there is a particle production. You're seeing this, non-analyticity related to particle production. So there's a cut here that connects these two singularities. Moreover, there's the E-total pole. And the E-total pole is somewhere here in the middle. So there's minus V is somewhere here. So now that it's a cut, it's remember that I told you that the singularity is always as U plus V goes to 0. But in the flat space example, the toy example that we studied, it was a pole. But now it's a cut, and then what you're supposed to do is supposed to take the discontinuity. Okay? So here the discontinuity at the cut at the U as U plus V goes to 0 goes like 1 over S flat. While here the thing factorizes, so you get log 1 plus U times G times the shifted wave function is a function of V. Remember that that's the factorization limit, right? You take one of the points and you put it very, very far away from this guy. So this happens in flat space, essentially G, while this gives you the shifted wave function. Okay? Because there is non-analyticity, right? So there's a log. This you have to look at the structure of the differential equation to see. In the flat space analysis, everything was clean because everything was poles, so there was no cut. I mean, the cut, strictly speaking, can disappear if the particles that you're considering are very special values of the mass. So for example, if you consider this diagram, but you do photon exchange, the solution is rational, okay? Then there's no cut, everything is poles. But for a generic mass, instead of having poles, you have a whole cut, okay? So there's something that people use in ADS called Melling space. I don't know if you're familiar with it. In Melling space, then the claim is that all singularities are poles, but there are infinitely many of them. So here in momentum space, they kind of get condensed. The infinitely many poles get condensed into a cut. Just like you can, if you regularize a little bit the log, you can see the log is an infinite number of poles that kind of coalesces into a cut. Okay, same story is happening here. So this is the analytic structure for generic mass. Okay. Let me make one comment. I didn't say because I did not analyze the equation in detail, but it goes like U plus V log U plus V. Okay, here in this limit. While here it goes like U to the I mu essentially. Okay, and there it goes like log of 1 plus U. So it depends on where you are on the cut. Okay. Remember that mu squared plus a quarter is m squared over h squared minus 2. So it only opens a cut for generic mu. Sometimes it can be just a positive law, in which a positive power, in which case there's no cut. Yeah, the u plus v log u plus v is not difficult to convince yourself of. Let me see if I can quickly sketch. You write delta u plus mu squared plus a quarter f goes like uv over u plus v. So you see it has two derivatives here, right? There's d2u. As u goes to minus v, nothing happens to the operator, right? So it's not like there's something funny going on with the coefficient. The coefficient was like u squared, 1 minus u squared. What's happening is that this guy is blowing up. So focus only on this guy. So it's like d2u f goes like 1 over u plus v as u goes to minus v. Integrate once, log. Integrate twice, you get this. Okay. So that's neat also because, well, we know that in scattering amplitudes, massive exchange softens the high energy behavior of the amplitude, right? Compared to hard scattering, that the amplitude grows. Instead, if you have a mass scattering amplitude with exchange of a mediator, the high energy behavior gets softened because it's like 1 over s. So remember that we got u plus v poles in all these contact terms. U plus v cubed, u plus v to the fifth. Instead, for an exchange solution, it's a softer behavior. It's logarithmic. It's the derivative that blows up, not the function itself. Okay? So that's something that the de Sitter correlator knows that the flat space amplitude doesn't really know, or the flat space wave function. The order of the pole, the order of the singularity tells you something about the the high energy behavior of the corresponding scattering amplitude. Okay, the softer the amplitude is, the milder the singularity is. And I'm going to get back to that in 20 minutes. This is an important point. No, no. It's this is a single particle exchange. So it's the analytic structure of single particle exchange in the Sitter space has a cut. It's not like in flat space where single particle states are poles. So, yeah, does it mean anything in a deeper level? I don't know. I don't know if maybe asymptotic states are always fuzzy in the Sitter. I don't know what. But I'm just telling you that at 3 level, this is what you get. Okay. So it's very different than the. So the analytic structure of contact terms, contact interactions in flat space is completely smooth, analytic everywhere. In the Sitter space, you have poles in only one location, E total. Here, the claim is that you have singularities, a guaranteed singularities at least at 3 locations, in the u minus v and minus 1. But then what ends up happening when you impose all of these things is that you open up a cut. Okay. I don't have any good physical interpretation of the meaning of the discontinuity. So it's not that the discontinuity is constant along the cut. The discontinuity changes. You see, when you approach from here, you get the log. When you approach from here, you get the flat space amplitude. So I don't know if there's interesting. Here it's particle production. I don't know if the discontinuity for u in between has some interesting physical interpretation. I never thought about it. Okay. So now, if you were keeping track, we are on point 12. I just want to say this is a bit technical, so I'll say very little. But you know, given that it's a string theory school, maybe you might find this interesting. So we solved the 4-point function for conformally coupled scalars and for exchange of a scalar particle. So what happens when you change the mass of the external particle from 2 to 0, from m squared equals 2h squared to m squared equals 0, you change the decay rates eta to the delta equals 1 to eta to the delta equals 0. Or you change the wave function coefficient psi for operator of dimension delta tilde equals 2 to the wave function of operator with delta tilde equals 3. Okay? They always add up to the number of spatial dimensions. So, so why are these guys connected to each other? Essentially because these are integer. It's just 2 plus 1 equals 3. Now we're here, you saw the Pontecorvo could write 2 plus 2 equals 5. I would just write 2 plus 1 equals 3 here. I don't know if everyone's seen the picture, a memorable picture. So this is called when you can connect these guys. There is, well, okay, let me start with almost trivial observation that if I write 1 plus I k eta e to the minus I k eta equals 1 minus k dk e to the minus I k eta. So there is, which is almost, it's not quite, but it's almost like the conformally coupled mode function, okay? 1 minus k. You can do better than this, or can do much better than this, but just to illustrate the point, okay? So phi classical, var phi classical. This is not true, okay? There's an eta here, but I'm just trying to be impressionistic. So there is an operator that depends only on momenta, not on time, that if you act on the conformally coupled correlation function, it will give you a massless correlation function. So if you have 4 points, you just sprinkle this on point 1, point 2, point 3, point 4. Okay? You can just build this by brute force, by looking at the expression in perturbation theory, the time integrals that you would get, and then trying to see if you can reverse engineer from the conformally coupled exchange diagram the massless exchange diagram, because that's what we care about, right? We want to study massless particles to discuss the early universe. Actually, it turns out that the moment you add spin, so this is one thing, so this is mass weight shifting. But then, okay, there was this beautiful story about massive exchange, but what about spin? Spin exchange. So let me give you a little cartoon. Let's couple the scalar field to some spin 1. Okay, so we need to charge them. So you couple them to gauge field, a mu. So there's a cubic coupling, and then you write then you have cosmological correlator where you exchange now spin 1 particle like this. Now I'm still doing conformally coupled, but I want to exchange a spinning particle instead of a scalar particle, okay? Now, what's the idea? This A mu, it has a spatial index and a time index. So there's AI, A0. So the A0 part, you just get time derivatives here, and time derivatives of a mode function that is as simple as a plane wave, you can just replace more or less k derivatives, okay? So it seems that, so what is the goal? The goal is, wouldn't it be nice if you could write some operator that depended, now we have k1, k2, and the gauge field A has momentum ks, okay? Wouldn't it be nice if there was something that depended on momenta that you can then sprinkle on something that looks like phi 1, phi 2, sigma, scalar particle? Because then you can recycle the scalar exchange result, sprinkle it with derivatives, and then get the spin exchange result. Okay? Wouldn't it be nice? It would be. And actually, I remember exactly where I was when I was in Greece. And then on the beach, very nice. Then I pulled the paper. I'm like, I've been struggling with this stupid diagram for like 6 months. And then, very interesting. So it turns out that you can write some operator that now the novelty is that, remember that there was K1, K2, K3, K4, Ks, and we dropped KT, right? But let's, what's the true signature of spin? How do you know that you go on the S channel, boom, produce a resonance? How do you know the spin of the resonance? So I just showed you here. You detected, I give you a mini particle accelerator. You go, I detected the Higgs. But you don't know the spin of the Higgs. How do you test if it's a scalar, if it's spin 1, if it's spin 2? What are you supposed to do? How? You only have scalars, and you're scattering scalars, right? The external particles are scalars. What is it that you can do with the? Well, is there another thing you can play with besides the center of mass energy of the process? You have a detector, no? What's the shape of your detector? What's the shape of the LHC? Yes, circle. It's a circle. So there's things get smashed, and then they go off in different angles. Yes, yes. So the angular dependence. So you boost to the center of mass frame. Stuff comes in, stuff comes out, and this is what we haven't looked at. So how does it depend? How does spin affect the answer? It's representation theory. Representation theory. How? You already found the pole. It's the location of the resonance. That gives you the mass. Is that as you move around, you see that more stuff is deposited. Like there will be, it's not that stuff is deposited uniformly in the detector, right? It's deposited. There's like bunches here, bunches there, and then you form a pattern, and that's how you measure spin. That's the point. The point is that even if you're on the S channel, the T Mandelstam appears in the answer. So what is the answer in flat space? Is G squared S minus M squared, and then there's some prefactor. What is the name of this P, this function? What do you think? Hmm? No, it's too fancy. It's the Legendre polynomial. The Legendre polynomial Pj of cosine theta. And this you can, I hope you've been having lots of steak. This is the, you can do tonight after maybe you get some nice pasta al tartufo in the Mercato Centrale in Firenze. Very nice. This is the answer, okay? Actually, how do you bootstrap this answer? Do you know how to bootstrap this answer? Without touching, no Lagrangian will be harmed to find the result of this scattering amplitude. So how do you find it? Come on, no. Simple. Reggie theory. No, Reggie theory is this on steroids, no? Simple-minded people. What happens when you sit at the resonance? What happens when you sit at the resonance? What happens to the amplitude? It doesn't vanish, no, it's blowing up. So, but more importantly, you're putting the particle on shell, so it can travel arbitrarily long distances. So it factorizes. So everyone loves ADS-CFT. So you know, 3-point function of 2 scalar primaries and 1 spinning primary. Is it unique at 3 points? 3 scalars everyone knows, the Polyakov formula. So 2 scalars and 1 spinning particle, is it unique? Come on, ADS-CFT people. Is it true? Yes or no? It's a yes or no question. Who thinks yes, it's unique? Yeah, only one person thinks you. Everyone else, should I apply the exclusion or there's an extra component? It's unique. Yes, it's unique. What is it? The scattering amplitude, because of this total pole story, is also unique. Poincare symmetry is so powerful that at 3 points on shell, the scattering amplitude is unique. What is it? So you have some polarization data of your spinning particle, epsilon mu. Let's do spin 1, okay? K3, K1, K2. What's the scattering amplitude? There's only one thing you can write down. What is it? Okay, let's go. I'm the one that is a little bit banged up today. Come on. Let's go. 3 massive scalars. What's the scattering amplitude? What's the kinematic dependence on the scattering amplitude? In terms of P1, P2, P3. Flat space, forget the sitter. Nothing. P1. I'm teaching the first 20 minutes of the amplitudes course. Zero? No. Why? P1 plus P2 plus P3 is 0. But you can build Lorentz invariants, no? So what is the scattering amplitude? P1 squared equals M1 squared, P2 squared, M2 squared. So how many scattering amplitudes can you build? 1, 2, 3, infinity, 0, half, e to the I theta. The answer is 1. What is it? What is the only thing you can build? Just a constant. That's the only thing you can build. It can be the masses also, but it's just a constant. Why? Give me a Lorentz invariant. Why can't I build this? What's wrong with this? Why not? We are on the translation invariance, it's just that the p's add up to 0. What's wrong with that? That's Lorentz invariant, P1 dot P2. So what? You charge the scalars. Yes. Yes, they're massive, therefore. Sorry. Okay, let me do it slowly. Where's that? No, it's not 0. So P1 dot P2 is P1 plus P2 squared minus P1 squared minus P2 squared, right? Let me put a 2 here. Then what is P1 plus P2? Minus P3, P3 squared minus P1 squared. But they're on shell. Just M3 squared. It's just a constant. It's some constant. Doesn't matter that it's the masses. Whatever you build, you're just gonna get a constant. Okay? This is the flat space analog of the Polyakov formula, that the 3-point correlators of conformal primaries are unique. OPE coefficient. This is the analog of OPE coefficient. Okay? OPE coefficient for amplitude is just a constant. Okay. So you can tell Marco Chiodaroli that the first 20 minutes he can skip. So let's continue. Let's make the third guy spinning. So now you have one new thing. You have the polarization. So how many amplitudes do you have now? 1, 0, 2, 3, infinity. Hmm? 1. What is it? Polarization, good, times what? It needs to be a Lorentz scalar. No, it's an amplitude. Which momentum? Which combination? 1 plus 2 is minus 3, P3 dot epsilon 3, 0. Pronto. That's it. That's the only thing you can write down. What is the amplitude for a spinning particle of any spin? What is it? Yes. Okay, very good. So, How do you bootstrap this amplitude? It has a pole. When you sit at the pole, you must get product of 3-point functions. We just argued that the 3-point function is unique. You write the 3-point function on the left, the 3-point function on the right. You sum over polarizations, right? Because the polarization here by angular momentum conservation needs to be the same as here. What is the sum over polarizations called? If you have a momentum in this direction, you sum over all polarizations in the transverse plane. What's this object called? Letter, U, letter. Yes, Y, E, and S. Y. S. Ah, bravo, projector. It's just a projector. So this thing is going to be the projector in the S momentum, okay? Now it's a cute exercise to write down the contraction of the projector with S number of indices on the transverse momentum Ks, contracted K1 minus K2, K3 minus K4. And this you can do after steak or after tartufo tonight. You get the Legendre polynomial. Okay? And the new element is that you get K1 mu minus, or P, doesn't matter. You get P1 mu minus P2 mu dotted with P3 mu minus P4 mu. So this comes from the projector. And this goes like T. Okay? So, long story short, what is the avatar of spin exchange? It's T to the J. Okay? Because Legendre polynomial of order J. So, something that goes like T to the J divided by S minus M squared is characteristic of exchange of spin J of a resonance of mass M. Okay? That's how you read off the quantum numbers of your particle. You dial the center of mass energy, you find a resonance, you sit around the resonance, you scan in the scattering angle, and you see a Legendre polynomial behavior. And this Legendre polynomial behavior is just geometry. So this goes through in de Sitter space. Okay? The same story will go through now that it's not 4 momenta, it's just 3 momenta. Okay? So what it implies is that this KT will appear. But it's not going to appear, so you see this KS was all over the place because this variable U and V, they were defined by KS divided by K1 plus K2, or KS over K3 plus K4. So the KS dependence is very complicated. But the spin dependence in the T variable is identical to flat space. It's going to be a polynomial. So you have a polynomial in the T variable times a complicated function in the U and V variables. Okay? So that's the signature of spin. Now it turns out that if you sit on the beach in Greece for long enough, that you can find the differential operator that maps these two things, one to the other. And then you go one day and meet a colleague that knows a lot about conformal field theory, and you say, this has been known forever in conformal field theory. It's called weight shifting operator. So now comes weight shifting operators. So we were kind of reinventing the wheel, like banging our heads, like playing with bulk Lagrangians. Now, it's some fun representation theory statement about the conformal group that there are, so if I give you a correlation function of conformal primaries, okay, of dimension delta 1, J1, point x1, this is regardless if it's a position space, momentum space, this is not important. Then they need to be bilinears. Okay, there's a technical reason for it. It's hard to build conformal covariant operators that depend only on one coordinate. But you can build bilinears. They depend on pairs, x1, x2. These are simple operators. They involve x1 dot x2, ddx1, ddx2, and you can classify them by group theory. And it just comes from a fusion of Young tableau, okay, some stuff like that. Some boxes collide, blah, 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 decompose them. You get a family of possible weight shifting operators, okay? Then you have a menu of them, and when you hit a correlation function of delta 1, J1, delta 2, J2, then you can get depending on what you choose. So for example, you have 4 labels, okay? It tells you what you do to x1 and what you do to x2. I give you one example. Minus 0, minus 0, or plus 0, plus. So this would be the weight shifting operator that shifts the mass dimension by this guy by 1. The spin doesn't change. This guy here by 1. Spin doesn't change. Okay? So now you're cooking, right? You don't need, if you know these guys, this works inside of any correlation function. So you can take the conformally coupled exchange, which is every operator has dimension 2 and spin 0. And you have a menu of possibilities, so you can raise spin, you can raise weights here, lower weights there. There's a finite menu, I don't know, 6 or 7 such operators. You play with all of them in the hopes that you will land in a place where you spin up or change the mass of your field, and you don't need to solve any equation again. So for spin 1, for example, the bottom line is that there's a neat ansatz that looks something like this. So there's some projector that depends on the t, on the momentum t. It's linear in t. Remember, that's the characteristic of spin 1. Then it depends, of course, on the k1, 2, 3, 4, and s, ks. Let me call it kt. The important thing is that it's linear. The 1 is just that it's linear in kt. It looks something. Then there's some other thing that projects you onto the longitudinal mode, does not depend on kt, depend on k1, 2, 3, 4, ks times delta u f. So this is f, j equals 1. So now it's going to depend not on u and v, it's going to depend on u and v, in all of these other variables. Kt is going to depend on k1. Remember that u had depended only on the sum, k1 plus k2. But now you can depend also on k1 minus k2 because of these types of contractions here. If you contract k1 minus k2 with itself, you get k1 squared minus k2 squared. So, but this all comes from group theory, and you get something that looks like this. This pi is just the result of applying this weight shifting operator to the 4-point. So this is the 4-point function of the scalars, the one we've been discussing last lecture. And then you stick in some scalar particle here. And so if you stick in the solution I was drawing the analytic structure of here, then I claim that you get the diagram where now the blue particles don't change, but you spin up the internal particle. This particle now has spin 1. Okay? Each particle here corresponds. Remember that the wave function coefficient is the wave function coefficient that multiplies For example, for these phi's would be phi 1, phi 2, phi 3, phi 4. And then you can think of it as O1, O2, O3, O4. And these are the operators that I'm acting on. Okay? This works inside any correlation function. Now you add O, like OPE. This is an operator statement. And you don't touch particles 3 and 4. And then this is a true equation. I just wrote the operator equation. Then you stick it in whatever you want. So you can operate on particles 1 and 2 and change their quantum numbers. You can also operate on particles 3 and 4 with another weight shifting operator and change their quantum numbers. I just wrote the building block. You can use it as many times as you want. Sometimes you need to do it multiple times to land in the right spot, just because of the menu of weight shifting operators that you have available. No, in this case, I just gave you an example in which I changed the weight. I moved from conformally coupled to massless. But you would, for example, try to change the spin of. For, no, that's this is the general statement of weight shifting. I'm just saying that there are various of these guys that exist. I just wrote one example. There's like 6 of them. And now you're supposed to, I'm just telling you the result. If you apply enough of these and you sprinkle them in the right places, then there are 2 options. You buy that this formula exists, that I just pulled out of my hat, or I'm just showing you that what's running behind the scenes is this structure. If you apply enough of these, you land. Because this formula looks crazy. I mean, I didn't open this up, but this is some polynomial. It looks kind of far-fetched. You can check the boost symmetry is compatible with this as long as this. So that's to say that this whole ansatz that I just pulled out of my hat is compatible with all the de Sitter isometries as long as this function f solves our old friend delta u minus delta v equals 0. Okay? So if you take anything that solves this equation, sticking to this complicated ansatz, it's also conformally invariant. I'm just giving you the physical interpretation. It would be, because it's linear in KT, it would be some object that knows about spin 1 exchange. Okay? And you buy these ansatz, great. But if you don't, then it comes from here, from this weight shifting story. No, I don't want to explain it here. That's it. It takes some work. The way to do it is fair question. You write O. As usual, CFT, you can write some sort of partial wave decomposition. Sum over O intermediate, let me call O tilde delta. It's scalar exchange, so I'm doing O tilde delta 0, O tilde delta 0, O. And then I need to integrate. This is a projector. Okay, I'm just inserting the identity here. Divided. Sorry, this I did bad board management. O1, O2, O3, O4. Now I include the projector here. 1. Projecting only onto the scalar sector. I get some coefficient, some conformal block stuff. O1, O2, O delta, O3, O4, divided by O delta, O delta. Now you can spin up these guys using weight shifting operators. You apply weight shifting here, and you spin both of these up. The problem is that it depends on a coordinates that you don't have access to. You only know about K1, K2, K3, and K4. And then you need to use some conformal symmetry magic to trade the operators that act on these guys by operators that act on these guys. Okay? That's why I didn't explain to you. But that's a fair question. It's not trivial to get there. But so let me give you an example of, let me do photon exchange, okay? Four scalars exchanging massless spin one particle. The photon, a mu, has delta equals 1 or delta equals 2. Just like the conformally coupled scalar. Same dimension as the conformally coupled scalar. Do you remember why I mentioned this to you a couple days ago? Why the photon is massless? Why doesn't it have delta conformal dimension 0? Why? Remember I mentioned the problem of magnetogenesis? You don't particle produce photons in de Sitter space. Why? Someone had responded, you forgot the answer. This is the Maxwell action, right? What happens if I rescale the metric by conformal factor? This cancels, no? So it doesn't know that it's in de Sitter space. It's like a conformally coupled scalar. It's the same answer as if you were in flat space. So it decays like a massless scalar field would, conformally coupled field would in de Sitter space. So delta equals 1. So then you can just take the m equals 2 answer. But remember, the equation in that case becomes delta u f equals uv over u plus v. Great. So you don't even need to know the answer. You can already compute this part here. So I give you the full result. So fj equals 1 for photon exchange is given by this. There will be this projector, pi 1. Then now there's another neat thing that happens. uv squared du dv f. I didn't write f for you, okay? It's a polylog, the answer. I'm not telling you the explicit formula. But this is kind of neat. It's given by, I think this u plus 1, v plus 1, u plus v. Enough power of ks here. No, I think 1. This formula here should remind you of what we discussed about the flat space exchange correlator. U plus 1 is related to the left energies. V plus 1 is related to the right energies. This is like K1, 2s, K3, 4s, K1, 2, 3, 4. Okay? So you get pi 1 times 1 over u plus 1, v plus 1, u plus v, plus pi 0 times delta u, but delta u on f is uv over u plus v. If I told you this is, I'm exchanging a particle in de Sitter space and this is the answer. How would you argue that it's the photon? KT is u plus v, huh? KT is in both. No, you mean sorry. KT is here in the projector. So spin 1 particle. The spin 1 part has partial energy singularities. U plus 1, V plus 1 going to 0. So it propagates a spin 1 degree of freedom. The spin 0 part only has K total singularity. So does that ring a bell? That's what the photon is all about. No, it doesn't carry longitudinal degree of freedom. This is the longitudinal mode. This is the spin 1 part, the helicity 1 part, and this is the helicity 0. But it's not that the helicity 0 part is absent. There is a contact helicity 0 part. What's that known as in the literature? What is the spin 0 part of photon exchange? It's the longitudinal component. It's also known as you. Letter V. Letter L. Okay, good. Yes. Letter E. E as in Empoli. A. A. O. YOLO. Who is French here? So, si. It's the Coulomb force. It's the speed. What is the longitudinal part of the photon? It's the Coulomb. Is the. You have to solve for the Gauss's law, the static potential, the constraints of electromagnetism to start with. So you can't just put charges and be done with it. So this is the Coulomb potential that is due to the charged particles. So actually, for all for special masses in de Sitter space at higher spin, you can read off the degrees of freedom. So for the graviton, for example, there would be spin 2 part that has the left and right poles, the E total pole, and then the spin 1 and spin 0 part have only this E total singularity because it's related to the Gauss's constraints of GR. The longitudinal part is the Newtonian potential. Okay? Yes, but I don't think, maybe Raja was thinking about it. No, I don't think people have, yes. The answer is yes, but nobody has done it as far as I know. Okay? Of course, you always have to bring them in pairs, otherwise, you see, this always produces an answer that is compatible with conformal symmetry, but sometimes the answer is 0, right? So you need to make sure that you don't force the answer to land on 0. You think you're doing the right thing, but then you get, I mean, it's compatible with conformal symmetry, but it's not interesting. So as long as you do things in pairs, then you can produce fermion diagrams. Okay. Enough about this. I will talk about phenomenology and then I think I'll stop. And tomorrow I'll hijack a bit of the question session and then do a full lecture. So, phenomenology. So how do you use cosmological correlators to? So this is also known in the literature as cosmological collider physics. Cosmological collider physics. So how do you read off from cosmological correlators different types of physical scenarios? Okay, so we discussed mass and spin, right? So that's the first thing. So just to write some formula, something a little bit more, slightly less sketchy, still sketchy, but not super sketchy. If you take the correlator now and you exchange a certain particle, so the 3-point function of the curvature perturbation, what you would really see in the data, okay, it would look like this. It would look like 1 over K1, K2. The easiest way to detect a new particle is to create a hierarchy between the momenta, okay? So that you give it many Hubble volumes to travel, as we discussed. So I'm going to assume that K1 is much smaller than K2, is order K3. So in these soft limits, this 3-point function will go like this. K1 over K2 to the delta, to the leading fall-off behavior of the, yes, I've been using this yellow, where m squared over h squared is delta minus 3 with an import. So this is the usual formula for ADS-CFT relating mass and conformal dimension, but think that here, when the mass is big enough, this needs to be complex, so there's a minus sign, okay? So for light enough masses, the solutions are real. For heavy enough masses, the solutions go off into the complex plane. So for delta real, you're supposed to take the leading, the smallest value of delta to stick in here. And then there will be a Legendre polynomial behavior, Pj, of cosine theta, where now theta is just going to be the angle between momentum 1 and sorry. Yeah. It's K1 dot K2 over K1 K2. It's cosine theta. Okay. So this is how you read off. So this is how you do spectroscopy in the 3-point function. You see, as you create a hierarchy between long modes and short modes, this is fixed just by dilation, by scaling of the final answer. But then the fall off, the smaller delta, the slower it falls off. As it falls off as K1 goes to 0, K1 over K2 goes to 0, the slower it is, the lighter the particle is, okay? And if it's massless, a strictly massless limit, there is no fall off whatsoever. Remember the statement a few lectures ago about detecting this type of coupling between long modes and short modes is smoking gun of a new light state, okay? Now, if you go and measure the angle, if you take these 2 points and move them around, you can think of them as a polarimeter. So you see the signal modulating, going up and down. There will be Legendre polynomial behavior that goes like the cosine of the angle between the momentum 1 and the momentum 2. Okay? In the case that the dimensions are complex conjugate, there's no leading fall-off behavior. So for m greater than 3/2 h, then you get 1 over K1, K2 cubed. You get K1 over K2 to the 3/2, and then you get cosine of mu log K1 over K2 plus some phase. The phase is interesting because it's related to particle production, right? The relative size between the e to the IMT and e to the minus IMT in the 2-point function. Okay. So I'm just writing the two delta contributions and adding them up. So I get some envelope and the oscillations. Unfortunately, for the real world, if you really want to detect this, the oscillations are logarithmic, so you would need a very long baseline, very big ratios to be able to see the oscillations, okay? And moreover, you can imagine compensating by cranking up the mass, but at some point, if the mass is too big in Hubble units, you pay Boltzmann suppression, right, to create a very heavy particle. So this mu cannot be, you can make it maybe order 100 with some model building, but it cannot be, a billion, so that oscillations are happening over many times over the scales that we can probe. So this is how you do spectroscopy for mass and spin. This you can more or less read off from the analytic answer in the Sitter space. Actually, even searching for spin has not been fully exhausted in data. So maybe we haven't heard the last about spin. So this is a relatively recent development. So the second thing is tree versus loop. So loops are very interesting because we don't know how to compute them, but also because standard model fields can, if the inflaton is neutral under the standard model, you can imagine still writing some operator that couples them to overall gauge charge 0. And then having the standard model run in the loop. Like say you have a Higgs, 2 Higgses run in a loop here, and or the fermions of the standard model, some Yukawa couplings and so on. So loops are very interesting for phenomenological reasons, but mathematically they're very interesting because we don't know how to compute them. So we have this machinery to deal with trees, but the moment you add the loop measure, we haven't found still the right language. Maybe the most important thing is that it's a big opportunity, okay? We don't know how to compute loops. It's embarrassing, but it's true, okay? Because the integrals do not look at all like loop integrals there. The propagators are not rational, right? The propagators are products of Hankel functions. So it's products of Hankel functions where the argument you're supposed to integrate over some phase space. And it doesn't look at all like, even when you massage, in the last lecture, I'll show you a toy model where you can massage things so that it looks like flat space. But then the loop measure messes things up. So we don't have any presentation of loop diagrams where the known techniques help in an obvious way. Then you can play, maybe I'll just say it in words, you can change the symmetry breaking scenario. So for example, if you measure non-Gaussianity tomorrow, after we celebrate, we need to decide what's the model of the universe. And very likely, it's not going to be a model with de Sitter symmetry, because de Sitter symmetry, remember, to have this diagram here, and you will be very small in the de Sitter invariant theory, because remember that it came from taking a 4-point function of soft limits. But you're trying to keep hard momenta around with soft momenta, and there's only one time in which the interaction happens. So you always pay a price here. So these tend to be very small in de Sitter invariant theories. So you probably need to break boost symmetry. The simplest way, there are various ways of doing it, but maybe the most famous one, actually motivated by string theory. If you study the DBI action of a brain and so on, naturally gives rise to scalar perturbations that have a dispersion relation that is not relativistic. So if you give this curvature perturbation the speed of sound, then you create a hierarchy between the Hubble scale, the de Sitter radius, and the sound radius. Okay, so you have the de Sitter radius. So this is related to speed of sound, but more generally about de Sitter symmetry breaking. Okay, so you have the de Sitter radius, but when the speed of sound is much less than 1, then you have a sound radius. Okay, it's CSR, RDS. So what happens is that particle production happens at a smaller scale, but interactions, self-interactions tend to be local. So therefore, the perturbations don't really redshift much by the time they are being particle produced. So you tend to get an enhancement of non-Gaussianity, okay? So what happens in practice is that the coefficients that appear in front of the answer, what we were calling F and L, tend to be of order 1 over CS squared. So if you make the speed of sound 10% of the speed of light, you can enhance this to order 100. Make it be almost even ruled out. So if it's too subluminal, it's even ruled out, okay? So the scalar perturbations, if they are subluminal but at the 10% level, you can have non-Gaussianity around the corner. Now, you would have thought that this whole story about differential equations and so on used de Sitter symmetry. So the moment you throw symmetry down the drain, the differential equations go down the drain. Is that true? Actually, I thought so, but many people were criticizing this approach, saying, well, okay, very nice in the Sitter space, but it's not going to work in something more realistic. And then you go study models that have small speed of sound, which is what cosmologists really care about, people that want to measure this. And the differential equations are there. They get dressed, they change a little bit, but they are still there. Why? Okay, I'll leave you hanging with this. So for tomorrow, you think about it. The other thing is weak versus strong coupling. So everything we discussed was about weak coupling. It's really more of a point of ignorance assumption. We can only compute things at weak coupling. We struggled with tree level. We can't do anything at loop level. Why the heck are we talking about strong coupling? You could imagine that the inflation is like QCD, that the scalar perturbation is like some light scalar mode, and there's a whole tower of resonances that comes from some strongly coupled sector and so on. That's completely possible. And strong coupling is something that has not been much analyzed in the literature. And there are methods to analyze it, right? So for example, people have looked at large N. So at large N, you can find solutions that are finite in the coupling constant, that are exact in the coupling constants with 1 over N corrections. So there's some work about computing, for example, like, or resumming bubble diagrams. What happens if you stick this in a correlator, right? So what happens if you take diagrams that look like this, diagrams that look like this, and then you stick them in a correlator? What does the answer change? More generally, you could imagine having some 2-point function that comes from your favorite model of strongly coupled physics. Comes from holography, comes from diamonds in the sky, I don't know. You have some calculational way of finding an interesting 2-point function. here, you could imagine coupling it weakly to the inflaton and computing this correlator. Or you could even do something more ambitious, embed inflation in some strongly coupled sector. And this is, I think, an interesting question. I'm currently studying this problem. Hopefully have something to report in the future. So for example, you can use holography to get some of these core candidate 2-point functions. And given that it's a school in string theory, I think I should say something about what I would call string inflation. This is a big question mark, okay? So there is something called string inflation in the literature. That's not what I'm talking about, okay? What people call string inflation in the literature is let's take some branes, some cycles, wrap them up, and then at low energies you get a potential, okay? It's just trying to reproduce the standard inflationary story of slow roll inflation with some scalar rolling down a hill, but the scalar comes from some fundamental string construction of branes, wrapped on cycles with fluxes and Great. It would be a UV way of informing what potentials are possible. But in the end, it's about just a scalar field rolling down a hill, okay? String inflation in this language is something, I think, much cooler, which is, we have the Hubble scale during inflation that we don't know what it is. The people are willing to bet that it is at the 10 to the 14 GeV scale, close to the gut scale. What if this is the string scale? Okay? What if the Hubble scale is of the order of the string scale? Then there's no derivative expansion anymore, but you could still imagine weakly coupled theory, meaning three-level theory, but with infinitely many resonances. So we know how was string theory born. People were studying S matrices and said, oh, wouldn't it be nice to have an S matrix with this and that property? And then Veneziano went and wrote down something that people a posteriori identified as string theory. So is there a correlator? So the question is there a correlator that has properties A, B, and C? If it does, then I say you discover string inflation. So this would be a correlator that exchanges an infinite tower of higher spin resonances, and the higher spin resonances are doing a very non-trivial job, right? What is the magic of the Veneziano amplitude? It's not that you're exchanging a bunch of higher spin fields. It's that they conspire in the UV to soften the amplitude. They soften it much faster than any QF quantum field theoretic UV completion could. QFT states, they just tend to soften things like 1 over S, right? But then higher spin fields, they actually make the amplitude grow. Remember that the amplitude grows like T to the J divided by S. So you need an infinite tower because the infinite tower is kind of killing this growth of all the higher spin guys. There's some magic cancellation, and then you get much softer behavior than 1 over S. You get exponentially decaying amplitude. Amazing. So can we find a similar story for correlators? So first requirement is it should be de Sitter invariant, meaning it satisfies the analog of this delta U minus delta V equals 0. Okay? First requirement. Second requirement is what is the analog of UV softness? Remember that the K total pole, when you send K1, 2, 3, 4 to 0, If it was very hard contact interaction, it was a very high order pole. If it was exchange of a massive particle, it was soft. It was logarithmic. And then you can do a little counting exercise to see how fast the amplitude is supposed to decay at high energies. And you can argue that there is no singularity. So this is the analog of the softness. So the amplitude is so soft that you think that you're going to go to the total energy singularity, and there's no singularity whatsoever. So in the k total plane, it should be completely smooth as you send k total to 0. This, I'm sure you can build many things that have this property, but it must have partial energy singularities. With positive residues and unitary EREPs. This is the tough thing. So what does the Veneziano amplitude do? You go to super high energies, it decays exponentially fast. Then it has an infinite number of poles. You sit on every pole, it factorizes, and the residue is positive. Okay? So the residue at every pole is positive. And then when you check, for example, in fact, day one after Veneziano guessed the amplitude, if you checked, you would have found that that to get positive residues, the dimension of space-time cannot be arbitrary. The number d equals 26 pops out of the Veneziano amplitude to ensure, well, strictly speaking, you don't get d equals 26, but you get d, I think, less than 26. But you see the 26 popping out of that amplitude because of demanding that residues must be positive, okay? Meaning you sit, so that's the statement that the amplitude factorizes. So you sit on every pole, there's a 1 over s minus m squared, but there's a g here and there's a g here. So the residue is g squared. It's not whatever you want. It's some positive number. So that's the requirement that sometimes you get when you go to spinning particles, you see dimension of space-time minus 26. Okay. So that's the, and moreover, well, strictly speaking, the Veneziano amplitude doesn't really achieve this goal because it has a tachyon, but okay, what's a tachyon between friends, right? So one of them fails, but all the others are unitary EREPs. So I would be happy if you can do it even with one. If you can do one unphysical particle and then an infinite tower of physical ones, that would be very nice. By the way, for Vasiliev theories, this 4-point function is known. It's been written down. And it would be nice, nobody has done it. It would be nice to just check all of these properties. That there we know the spectrum. The spectrum are just infinitely many massless particles. Just to check that all the residues are positive. I think that would be very nice. And the answer does not have any total pole. In fact, it's very simple. It's rational. Okay. So this is a challenge. You're string theorists, right? So if you can prove that such a function does not exist, it's also interesting. You prove that there cannot be something like 3-level string theory in the Sitter space. That I think would be very interesting. So that's also, this is related to, you could imagine there's some crazy strongly coupled world sheet model, and then this is a space-time that is super stringy, right? The string scale is at the Hubble scale. It's not the type of thing that people try to build in string cosmology, parametric separation of scales and so on. So you could imagine, it's not totally far-fetched, that there's some very complicated, strongly coupled worldsheet CFT that if you could study the target space spectrum would give you de Sitter space with all sorts of resonances. You would, if this 4-point function exists, then you prove that such a sigma model is probably there. Never mind that you found an amazing 4-point function that we can go and look for in the sky and test and so on. Great. I'm gonna stop. Tomorrow, we're gonna wear, for the first lecture, hat of a mathematician, and we're gonna talk about these differential equations. I'm gonna describe a toy model. There's only one particle in this toy model, but I'm gonna try to do any possible tree, okay? And if you massage the cosmological correlators at tree level, it turns out that you can bring them into something that looks very similar to loop scattering amplitudes. You were asking about doing loops. So tree-level correlators in the toy theory that I'm going to talk about tomorrow, they look like loop, more or less one loop, flat space scattering amplitudes. And then QCD people are absolute masters at this. They have enormous hammers to deal with this. And then I'm going to teach you about this big hammer. We're going to hit it with the hammer, but then there will be a surprise. Okay? So, see you tomorrow.